Hello there, and welcome to the Serene Scroll. I am so glad you are here with me tonight. Perhaps it has been a long day, filled with noise and haste, and now is a moment for quiet, for stillness. Here, we can let the weight of the day simply dissolve, finding a gentle space to rest the mind. Together, we are about to begin a quiet journey to the very edge of understanding a story written in the stars. And just before we begin, if these quiet explorations help you unwind or give you a peaceful way to end your day, consider gently tapping the like button and subscribing to the channel. It helps these stories find others who might be seeking a moment of peace. Now find a comfortable position. Let your breath soften, and let us begin. There is a profound and ancient stillness that comes with looking up at the night sky. On a clear, moonless night, far from the glow of cities, the universe reveals itself, not as a blanket, but as an abyss. It is a deep, velvety black, punctuated by the sharp, distant light of a billion suns. And in that vast darkness, the human mind has always sensed a question. What is it that fills the space between those lights? For most of history, the answer felt simple. It is nothing. A void, an emptiness. We saw the stars and the planets as performers on a stage, and the stage itself was just an empty backdrop, a passive silence against which the cosmic drama unfolded. This feeling of emptiness is deeply intuitive. When you drop a stone, it falls. It seems to be pulled toward the ground by an invisible tether. We feel this same pull, keeping our feet on the floor, holding the oceans in their basins, and keeping the very air we breathe from drifting away into the cosmos. For centuries, this was simply a fact of life, as fundamental and unquestioned as the rising of the sun. It took a mind of rare genius sitting in a quiet garden to ask, why? When Isaac Newton watched an apple fall from a tree, he saw not just a simple event, but a universal mystery. He wondered if the force pulling the apple to the earth was the very same force that held the moon in its silent looping dance around our world. His conclusion was a revolution. He proposed a universal law of gravitation. Every object in the universe attracts every other object. It was a beautiful, elegant equation that could predict the orbits of planets, the paths of comets, and the rhythm of the tides. It worked with astonishing precision. And yet, even for Newton, a deep puzzle remained at the heart of his discovery. How did it work? How did the sun, millions of miles away, reach across the seeming emptiness of space to hold the Earth in its orbit? How did the Earth know the sun was there? Newton called it action at a distance, but he famously refused to guess at its cause, admitting that the mechanism was a mystery beyond what he could explain. For over 200 years, gravity remained a ghost. It was a force that acted without touch, a command that traveled through the void without a messenger. It was a rule the universe obeyed, but a rule whose reason no one understood. We lived with this phantom, this invisible pull that governed our every moment, accepting its presence without understanding its nature. The emptiness of space remained just that, an empty stage. Then, in the early 20th century, another mind, a clerk in a Swiss patent office, began to look at the universe in a completely new way. Albert Einstein was not thinking about forces and pulls. He was thinking about the stage itself. He wondered if the emptiness of space was truly empty. He wondered if time was as constant as a ticking clock. And through a series of profound thought experiments, he arrived at an idea that would forever change our understanding of reality. He proposed that space and time are not separate things, but are woven together into a single dynamic fabric space-time. Imagine, if you will, a vast flat sheet of rubber stretched perfectly taut and held at its edges. This sheet represents space-time in a universe with nothing in it. It is smooth, uniform, and flat. Now take a heavy bowling ball and gently place it in the center of the sheet. The fabric of the rubber sheet immediately sags under the weight. It creates a depression, a smooth curved dimple in the otherwise flat surface. The heavier the ball, the deeper the curve. This, in essence, was Einstein's radical idea. He said that matter does not create a mysterious force that pulls other things toward it. Instead, matter tells space-time how to curve. And in return, that curved space-time tells matter how to move. Let's go back to our rubber sheet with the bowling ball sitting in its self-made valley. Now imagine rolling a small marble across the sheet some distance away from the bowling ball. If you roll the marble far enough away, its path is a straight line across the flat fabric. But if you roll it closer to the bowling ball, something beautiful happens. As the marble approaches the curved region, its path begins to bend. It is not being pulled by the bowling ball. There is no invisible string connecting them. The marble is simply following the straightest possible path through a curved space. It rolls down into the dimple swirls around the bowling ball and perhaps comes out the other side on a new trajectory. To an observer who couldn't see the curvature of the sheet, it would look exactly as if the bowling ball were exerting a mysterious attractive force on the marble. But from our higher perspective, we see the truth. Gravity is not a force. It is geometry. It is the shape of the universe itself. The Earth is not being pulled by the sun. The Earth is moving in a straight line through space-time that has been warped by the sun's immense mass. Our planet is like that marble, forever rolling around the deep curve created by our star. The moon, in turn, is rolling along the smaller curve created by the Earth. That apple Newton saw was not pulled to the ground. It was simply following the natural straightest path downward through the space-time curved by our planet's mass. This idea, known as the general theory of relativity, demoted gravity from a phantom force to a consequence of the universe's very structure. The stage was no longer empty or passive. The stage was the actor. The presence of matter and energy gives it shape, and that shape dictates the motion of everything that travels through it. The emptiness of space, it turns out, has weight. It has form. It has substance. This new vision of the cosmos allows us to understand another crucial concept, the idea of escape. Let us return one last time to our trampoline with the bowling ball, creating a gravitational well in the center. Imagine you are standing beside this well, and you flick a tiny bead into it. It will roll down and settle at the bottom, right next to the bowling ball. It does not have enough energy to climb back out. Now imagine you throw a small stone with all your might from the surface of the Earth. It travels upward, fighting against the planet's gravitational curve. For a moment, it seems to be winning, but its energy fades. It slows, stops, and then follows the curve back down to the ground. It did not have enough speed to escape the well. The depth of this well is determined by the mass of the object creating it and how compressed that mass is. Earth creates a respectable well. To climb out of it, to break free from our planet's gravity and travel into interplanetary space, an object must be traveling at a tremendous speed. This critical speed is called the escape velocity. For Earth, It is about 11.2 kilometers per second, or over 40,000 kilometers per hour. A stone thrown by hand cannot reach this speed. A bullet from a rifle cannot reach it. But a rocket with its powerful engines burning for minutes on end can accelerate and accelerate until it finally achieves that speed. At that moment, it has enough momentum to coast up and out of the gravitational well created by our planet, finally free to travel through the flatter space-time between the worlds. Every planet, every star, every moon has its own escape velocity. For our moon, which is much less massive than Earth, the escape velocity is only 2.4 kilometers per second. It is much easier to climb out of its shallow gravitational well. For the colossal Sun, the escape velocity at its surface is a staggering 618 kilometers per second. The well it creates in space-time is immensely deep. To leave the Sun's surface would require a vessel of almost unimaginable power. For decades, this was the framework. Gravity was the curvature of space-time, and every object had an escape velocity, a speed, however high, that would be sufficient to break free. It was a universe of wells, some shallow, some deep, but none infinite. The laws of physics seem to imply that there was always a way out, always a path to freedom, if only you could go fast enough. But then scientists began to push Einstein's equations to their absolute limits. They started to ask a dark and terrifying question. What if you could put enough mass into a small enough space? What if you had an object so incredibly dense that the well it created in the fabric of space-time was not just deep but bottomless? What would happen if the curvature became so extreme that the walls of the well became perfectly vertical? In such a place, the escape velocity would become higher and higher as the object grew more dense. It would surpass the speed of a rocket. It would surpass any speed we could imagine. And eventually, it would reach a final absolute threshold. It would become greater than the speed of light itself. And since nothing in the universe can travel faster than light, nothing could escape. Not a spaceship, not a particle, not even light. The path out of the well would simply cease to exist. Any light shining from the object would try to climb the curve, only to be bent back down, trapped forever. The object would become perfectly black, a hole in the fabric of reality, a place where the geometry of the universe has been pushed to its breaking point. This is the theoretical heart of a black hole. It is not an object in the traditional sense. It is a region of space-time that has become so distorted by mass that it has effectively tied itself into a knot from which there is no escape. The serene curves of planetary orbits become an infinite plunge. The gentle geometry that guides our world becomes a prison with walls that move at the speed of light. But for such an impossible object to exist, something in the cosmos would have to be capable of creating that much density of forging, that much mass, into an infinitesimally small point. The universe we see full of gentle stars and placid gas clouds seems too calm, too orderly for such violence. To understand how such an extreme curvature is possible, we must first look to the cradles of creation and destruction. We must look to the stars themselves, for it is not in their quiet shining lives, but in their cataclysmic fiery deaths that the seeds of these dark objects are sown. We must witness the most violent birth imaginable to understand the origin of this profound and silent emptiness. To understand a black hole, we must first understand the life that came before it. For every black hole is a ghost, the echo of something that was once impossibly brilliantly alive. Our story begins not with an end, but with a birth in the cold, quiet darkness between galaxies. Imagine a vast, silent cloud of dust and hydrogen gas stretching for light years across the cosmos. It is a stellar nursery, a place of immense potential, but for now it is mostly empty and profoundly cold. The particles within drift aimlessly, like motes of dust in a sunbeam that has not yet arrived. But they are not entirely alone. A silent, invisible force is at work here, patiently gathering them. This force is gravity. It is weak, almost imperceptible at first, but it is relentless. Over the course of millions of years, the gentlest of whispers becomes a command. Gravity coaxes the scattered particles of gas and dust into a slow, majestic dance. Tiny grains of cosmic dust clump together. Molecules of hydrogen find one another in the dark. The cloud begins to contract, swirling into vast, slow eddies. As it condenses, small pockets of density begin to form regions where gravity's pull is just a little stronger than elsewhere. These are the seeds of stars. Let us follow one such seed. In the heart of this swirling nebula, a clump of gas grows, pulling more and more material from its surroundings. Its gravitational influence expands its core, becoming ever denser, ever hotter. For thousands of years it is a protostar, a star in its infancy, shrouded in the dusty veil of its own cradle. It does not yet shine with its own light. It only glows with the heat of its own compression, a dim infrared ember in the cosmic dark. But as the pressure and temperature at its core continue to build, a threshold is approached. The crushing weight of trillions of tons of hydrogen gas creates conditions unthinkable on any human scale. The core reaches a staggering 10 million degrees Celsius. At this magical point, a new force awakens. A fire is lit in the heart of the cosmos. Nuclear fusion begins. In this moment, the protostar is truly born. It ignites. The core becomes a furious engine, smashing hydrogen atoms together to forge helium. Each of these reactions releases a tiny, powerful burst of energy in the form of light and heat. This outpouring of energy creates an immense outward pressure, a radiant force that pushes against gravity's inward crush. The star we are watching is no ordinary star. It is a giant born with more than 20 times the mass of our own sun. Because of its immense mass, its gravitational pull is ferocious, and so its engine of fusion must burn with unimaginable intensity to hold itself up. It shines not with the gentle yellow-white of our sun, but with a brilliant, fierce blue-white light. It is a blue supergiant, a celestial titan, a short-lived and spectacular monarch of its stellar neighborhood. For the next 10 million years, a brief lifetime for a star of this magnitude, it exists in a state of perfect, delicate balance. This is the star's long and stable adulthood. From the outside, it appears serene, a constant, unwavering point of light in the sky. But inside, a colossal battle rages. Gravity, the force of collapse, relentlessly tries to crush the star into a single point. Fusion, the force of creation, relentlessly pushes outward, providing the light and heat that keeps the star alive. These two fundamental forces are locked in a silent cosmic stalemate. During this time, the star is not merely shining. It is an alchemist's forge. In its core, it is creating the very building blocks of the universe. The hydrogen fuel is steadily converted into helium. As the hydrogen runs low in the very center, the core contracts further under gravity's pull, becoming even hotter and denser. This new intense heat allows the star to begin fusing the helium atoms themselves. A new chapter begins. Helium atoms, the ash of the first fire, now become the fuel for the next. They fuse to create carbon. The star develops a layered onion-like structure. In the outer layers, hydrogen still burns into helium. Deeper down, in a shell around the core, helium burns into carbon. The star swells its outer layers, expanding and cooling slightly, but its heart grows ever hotter. This process continues a cycle of cosmic creation, driven by the inexorable pull of gravity. When the helium is exhausted in the core shrinks and heats up again until it is hot enough to fuse carbon into heavier elements like oxygen, neon, and magnesium. Each stage of fusion is shorter and more frantic than the last. The burning of hydrogen lasted for millions of years. The burning of helium lasts for hundreds of thousands. The burning of carbon lasts for mere centuries. In its final 1,000 years, the star's core becomes a frantic furnace, forging ever heavier elements. Neon burns for a year, oxygen for 6 months, silicon for a single day. The star is creating the very elements that will one day form rocky planets. The calcium in our bones, the oxygen we breathe. We are, in the most literal sense, made of stardust forged in the hearts of stars, like this one. Finally, the star's alchemy reaches its endpoint. The silicon atoms fuse to create iron, and with iron, the engine stops. The fusion of iron into heavier elements does not release energy. It consumes it. For the first time in its long life, the star's core produces an element that cannot serve as fuel. The fire at the center of the world goes out. The balance is broken. With the outward push of fusion suddenly gone, gravity wins. It wins instantly, and it wins catastrophically. The iron core, now about the size of the Earth but containing the mass of more than 1.5 suns, has nothing left to support it. In less than a second, it collapses under its own colossal weight. The atoms themselves are crushed. Protons and electrons are squeezed together to form a super-dense ball of neutrons. The core, once the size of a planet, shrinks to a sphere no bigger than a city. This sudden, violent collapse of the core sends a titanic shockwave blasting outward through the star's overlying layers. The shockwave, combined with a flood of ethereal particles called neutrinos, reignites the surrounding material in one final explosive burst of fusion. The star explodes. This is a supernova. For a few weeks, our blue supergiant, now in its death throes, will outshine its entire galaxy. It will blaze with the light of 100 billion suns, releasing more energy in that brief moment than our own sun will in its entire 10 billion year lifetime. The heavy elements forged in its heart, the carbon, the oxygen, the iron, are hurled across space, seeding the surrounding interstellar clouds with the raw materials for new stars, new planets, and perhaps new life. It is a death that is also a creation, an end that is also a beginning. As the light from this spectacular explosion fades over months and years, a beautiful expanding cloud of gas and dust, a nebula just like the one the star was born from, is all that remains visible. But at the center of this cosmic wreckage, something else has been left behind, the remnant of the star's core. What happens to this remnant depends entirely on its mass. The Indian-American astrophysicist Subramanian Chandrasekhar calculated that if a remnant core is less than about 1.4 times the mass of our Sun, the crushed neutrons can push back against gravity, creating a stable, incredibly dense object called a neutron star. Gravity has been halted once again by a new kind of pressure. But the core of our massive star was much heavier than that. It was perhaps 3 times the mass of our Sun, all packed into a sphere just a few miles across. At this mass, nothing in the known universe can stop the force of gravity, not the pressure of fusion, not the pressure of electrons, not even the pressure of neutrons. The collapse does not stop. It continues on and on, crushing the core past the point of a neutron star, past any state of matter we can describe or imagine. The core collapses toward an infinitely small, infinitely dense point, a singularity. In this final ultimate victory, gravity becomes so powerful that it warps the very fabric of space-time around it. It digs a well in reality so deep that nothing, not even light, can escape. The violent, brilliant life of the star is over. The supernova's light has faded. The expanding cloud of debris drifts away into the silence. And here in the darkness, where a titan once blazed, there is now a new kind of presence. It is not a hole, but a destination. Not an emptiness, but a concentration of what was. It is a perfect sphere of blackness, a region of space sealed off from the rest of the universe, a ghost defined only by the gravity of the star it once was. The birth was violent, a spectacle of light and fury that lit up a corner of the cosmos. But the result is a profound and eternal quiet. An object has been created that has no surface, no texture, no light of its own. It has only a boundary and edge from which there is no return. To understand what this object truly is, we must now move past its fiery creation and dare to approach this silent perimeter, this anatomy of a ghost, to explore the strange new rules of reality at the event horizon. Where the brilliant, violent light of the dying star once raged, there is now a profound and perfect silence. A new kind of object has settled into the fabric of the cosmos, an entity defined not by what it is, but by what it is not. It does not shine, it absorbs. It does not radiate, it consumes. It is a sphere of pure, featureless black, a patch of velvet night cut from the star-dusted tapestry of the galaxy. This is the ghost left behind, an object of pure gravity so dense that it has torn a hole in the very meaning of space and time. To understand its anatomy, we must not look for it directly, but rather watch how everything else moves around it, how the universe itself holds its breath in its presence. Our guide on this journey will not be a spaceship or a probe, for no physical object could survive the tidal forces we are about to witness. Instead, our vessel is a single particle of light, a photon. Imagine it now, a tiny, massless packet of electromagnetic energy born in the heart of a galaxy a billion light-years away. For ages beyond human comprehension, it has traveled in a perfectly straight line through the near emptiness of intergalactic space. Its journey has been lonely and unchanging, a relentless sprint at the ultimate speed limit of the universe. But now, as it enters the gravitational neighborhood of this newborn black hole, its simple, ancient path begins to curve. At first, the deviation is subtle, almost imperceptible. The black hole is still millions of kilometers away, invisible to the photon. Yet its influence is already being felt. Gravity, as Einstein taught us, is not a force that reaches out and pulls things. It is a curvature in the very geometry of space-time. The massive star in its death has compressed its entire being into a point of near infinite density, and in doing so, has warped the space around it more profoundly than any other object could. Think of space-time as a vast, stretched rubber sheet. A planet like Earth creates a small dimple. A star like our Sun creates a deeper one. But this black hole has punched a hole clean through, creating a well so steep that its sides are nearly vertical. Our photon is now sliding along the lip of this cosmic well. It is not being pulled. It is simply following the straightest possible path through a universe that is no longer straight. From our distant, safe perspective, we can see the consequences of this warping. The light from stars and galaxies far behind the black hole is being bent around it. The effect is magnificent, a phenomenon known as gravitational lensing. The black hole acts like a giant, imperfect magnifying glass. The images of distant galaxies are smeared and distorted into strange, luminous arcs. A single star might appear in 2 or even 4 different places at once, its light having taken multiple paths around the ghost to reach our eyes. As our photon draws closer, the lensing effect becomes extreme. If its trajectory is just right, the light from its parent galaxy, a billion light-years behind it, is bent so perfectly that it forms a complete glowing circle around the central darkness. This is the Einstein ring, a halo of captured light, a ghostly wreath laid at the edge of oblivion. It is one of the most beautiful and eerie sights in the universe, the cosmos twisted into a perfect jewel by an object that cannot be seen. Our photon is now part of this celestial dance, its path bent almost 90 degrees as it skims past the invisible center of gravity. It is a near miss. It escapes continuing its journey, but it is forever changed, carrying with it a story of its close encounter with the ghost. But let us rewind and imagine a different photon, one whose path is not so fortunate. This second photon is on a direct collision course, not with an object, but with a boundary, a threshold. This is the most famous feature of a black hole's anatomy, the event horizon. The event horizon is not a physical surface. You could not stand on it or touch it. It is not made of matter. It is a purely geometric boundary, an invisible sphere drawn in space-time. It is the place where the gravitational pull becomes so immense that the escape velocity, the speed needed to break free, exceeds the speed of light. And since nothing can travel faster than light, this boundary marks the point of no return. It is a one-way door in the universe. As our second photon approaches this threshold, something extraordinary begins to happen, something that reveals the deepest and most bizarre connection between gravity, space, and time. And to understand it, we must watch from 2 different perspectives. First, let us remain as the distant, safe observer. We watch through our powerful telescope as the photon plunges towards the black hole. As it gets deeper into the gravitational well, it has to expend more and more of its energy just to keep moving forward, to climb out of the deepening curvature of space-time. This expenditure of energy causes its wavelength to stretch. Its light, once perhaps a brilliant blue or a pure white, begins to shift toward the lower end of the spectrum. It becomes yellow, then orange, and then a deep, tired red. This is gravitational redshift. The photon is losing energy not by slowing down, it cannot slow down, but by becoming a less energetic version of itself. Simultaneously, we observe another, even stranger effect. Time itself, from our perspective, begins to flow differently near the event horizon. Just as space is stretched, so too is time. As the photon gets closer and closer to that invisible line, we see its forward progress appear to slow. It moves from meters per second to millimeters to microns. The final approach takes an impossibly long time. It seems to crawl, fighting against a current that has become infinitely strong. To us, the photon will never actually cross the event horizon. It will appear to freeze just at the edge, its light redshifted into oblivion, becoming so faint and low energy that it fades from our view. From our vantage point, the entire history of an object falling into a black hole is smeared across its horizon for all eternity, a frozen tableau of its final moments. The event horizon is for us a boundary not just of space, but of knowledge. We can see up to the edge, but we can never ever see anything cross it. But now, let us switch perspectives. Let us ride along with the photon. What is its experience? For the photon, there is no slowing down. There is no dramatic pause at the edge. The event horizon is not a wall or a barrier. It is just a location in space. One moment the photon is outside, the next it is inside. It crosses the threshold at the speed of light, its fundamental unchanging velocity. There is no signpost, no jolt, no indication that a line of cosmic significance has been crossed. The laws of physics from its local perspective are still perfectly intact. For the infalling object, the point of no return is utterly unremarkable. This is one of the deepest paradoxes of a black hole. For the outside universe, the journey into a black hole takes an infinite amount of time. For the object making the journey, it takes a finite and often very short amount of time. Both perspectives are true. Time is not absolute. It is relative, and in the presence of extreme gravity, it can be stretched to the breaking point. Now our photon is inside. It has passed through the one-way door. And here, the anatomy of space-time is unlike anything we know. Outside the black hole, you are free to move in any direction in space, up, down, left, right. But you are forced to move in one direction, in time, forward into the future. Inside the event horizon, this relationship is flipped. The warping of space-time is so extreme that the roles of space and time have partially swapped. Now the dimension of space pointing towards the center of the black hole has become like a direction in time. All possible paths, every single trajectory that light or matter can take now points inward. You cannot escape the singularity for the same reason you cannot travel back to yesterday. The future is no longer a concept, it is a physical location, and that location is the center. The very geometry of existence funnels everything that crosses the horizon towards one inevitable destination. The photon does not need to be pulled by a force anymore. It is simply following the only available path through a reality that has collapsed in on itself. The universe it left behind is now quite literally in its past. Looking back towards the event horizon, it would not see the universe it came from. Instead, the intense gravity would so distort the light that the entire history and future of the external universe might flash before it in a distorted blue-shifted instant. And so, the photon continues its final brief journey. It is a journey of mere microseconds. All of reality is now converging on a single point ahead. The tidal forces grow infinitely strong. The fabric of space-time becomes infinitely curved. The photon is being drawn towards a second and final piece of the ghost's anatomy, the singularity. What is the singularity? Our best theories tell us it is a point of zero volume and infinite density. It is the place where all the mass of the original star, trillions upon trillions of tons of matter, has been crushed into a space smaller than a single atom. Here at this single dimensionless point, the laws of physics as we understand them cease to function. General relativity, our theory of gravity, predicts a point of infinite curvature and density. But this is really just the theory's way of telling us that it has broken down. It is a signal that we need a new theory, perhaps a theory of quantum gravity, to understand what truly happens at the heart of a black hole. The singularity is not just the end of the star. It is the end of our physics. It is the end of space and the end of time as we conceive of them. When our photon reaches this point, its journey is over. It is absorbed into the infinite density, its energy and information added to the mass of the black hole. Its story, which began in a distant galaxy a billion years ago, ends here, in a place beyond place, and a moment beyond time. We have now explored the anatomy of this ghost. It is an entity of breathtaking simplicity. It has only an outer boundary, the event horizon, which separates it from the rest of the universe. And it has a central point, the singularity, where the known universe ends. There is nothing in between. No structure, no surface, no substance, just warped space-time, a ghost defined entirely by its effect on everything around it. The object we have been studying was born from the death of a single massive star, a stellar mass black hole perhaps only a few dozen kilometers across. It is a solitary predator wandering the void. But this is just one example, one member of a vast and varied family. The universe, in its boundless creativity, has forged these ghosts in all manner of sizes, from the relatively small to the truly unimaginably colossal. The ghost of a single star is a fearsome thing. But what happens when a million or a billion stars worth of matter collapse into one? What kind of entity is born from such an event? The anatomy may be the same, a horizon and a singularity, but the scale and the role it plays in the cosmos changes completely. Our journey to the edge of reality has shown us one ghost, but a whole universe of them awaits. Where the brilliant, violent light of the dying star once raged, there is now a profound and perfect silence. A new kind of object has settled into the fabric of the cosmos, an entity defined not by what it is, but by what it is not. It does not shine. It absorbs. It does not radiate. It consumes. It is a sphere of pure, featureless black, a patch of velvet night cut from the star-dusted tapestry of the galaxy. This is the ghost left behind, an object of pure gravity so dense that it has torn a permanent wound in the page of space-time. We imagine this object, this stellar mass black hole, as a cosmic leviathan, a creature of unimaginable scale. But in the grand theater of the universe, this newly born entity is in fact one of the commoners. It is a foot soldier in an army of silent kings. Its mass may be 3, perhaps 10, or even 20 times that of our own sun, all compressed into a volume of terrifying smallness. Its event horizon, the threshold of no return, might span only a few dozen kilometers. If you could place it on the surface of the Earth, it would be no larger than a sprawling city, a silent, invisible sphere of absolute finality resting where London or Tokyo once stood. This is the standard model, the ghost we expect to find when a giant star exhausts its fuel. They pepper our galaxy, these stellar remnants drifting through the interstellar medium like seeds of darkness thrown from a celestial hand. Most travel alone, solitary pilgrims, on an endless journey through the void, their presence betrayed by nothing at all. But some are not so lonely. Let us pull our perspective back, like a camera drawing away from our city-sized sphere. We see now that it is not isolated. It is locked in a gravitational dance with a living star, a brilliant blue giant, that survived the supernova of its companion. The two circle each other in a hypnotic waltz that will last for millions of years. The black hole, with its immense gravity, is a patient predator. It begins to pull at the outer layers of its companion star. A shimmering stream of hot gas, a river of plasma brighter than 1,000 suns, is siphoned away from the living star and drawn toward the abyss. This stolen material does not fall straight in. Instead, it is caught in the black hole's gravitational whirlpool, forming a vast, flat-spinning structure around it, an accretion disk. Here, matter is accelerated to nearly the speed of light. Friction within the disk heats the gas to millions of degrees, causing it to glow with an intensity that can outshine entire star systems. It blazes in X-rays and ultraviolet light, a final desperate scream from matter on the verge of annihilation. The black hole itself remains unseen, but it wears this luminous, violent halo like a crown. It is a dark monarch fed by its captive subject. This scene, a stellar mass black hole feeding on its companion, is a dramatic but relatively local affair. It is a single household in the sprawling metropolis of the Milky Way. But just as cities have a center, a downtown district of immense density and power, so too do galaxies. And to find the true rulers of this cosmic kingdom, we must continue our journey, pulling our perspective back even further. We leave this binary pair behind their fiery dance, shrinking to a single point of light, then vanishing entirely. We drift past nebulae like watercolor clouds, through dense clusters of newborn stars, and across spiral arms painted with the dust of ages. Our destination is 26,000 light-years away, a journey that would take a beam of light longer than the entirety of recorded human history. We are heading for the heart of our own galaxy, toward the constellation of Sagittarius, where an object of a completely different order of being resides. Here at the galactic core, the universe is a different place. The quiet solitude of interstellar space is gone, replaced by a frenzy of activity. Stars are packed together 1,000,000 times more densely than in our own stellar neighborhood. They swarm like fireflies in a jar, their orbits chaotic and impossibly fast. And they are all orbiting something they cannot see, something vast, silent, and overwhelmingly powerful. This is the realm of the supermassive black hole. Our galaxy's central engine is named Sagittarius, a.k., a placid-sounding name for a cosmic titan. It is not 10 or 20 times the mass of our Sun. It is over 4 million times the mass of our Sun. All of that mass is contained within a region smaller than the orbit of Mercury. If the stellar mass black hole was a city, this supermassive one is a solar system unto itself. It is a different species of monster entirely. We cannot see Sagittarius AC, but we can watch its staggering influence. We can track the motion of the stars caught in its gravitational domain. One star, named S2, performs an incredible celestial ballet. It whips around the invisible center at over 7,000 kilometers per second. Nearly 3% of the speed of light, completing its elliptical orbit in just 16 years. It is a frantic high-speed dance dictated by a partner it can never touch. By charting the precise path of S2 and its neighbors, astronomers can weigh the unseen object at the center of their waltz. The calculation is inescapable. The only thing that could hold these stars in such a grip is a single compact object with the mass of 4 million suns, a supermassive black hole. And our Milky Way is not unique. As we pull our vision back even further, expanding our view beyond our own galaxy, we see that this is the cosmic rule, not the exception. We look toward Andromeda, our nearest galactic neighbor, and at its heart, we find a supermassive black hole weighing in at over 100 million solar masses. We gaze out across the cosmic web to galaxies millions and billions of light years distant, and we find them there too. At the heart of nearly every large galaxy we have ever observed, there sits a silent, supermassive anchor. Some are quiescent, like our sleeping giants. Others are active, known as quasars, ferociously feeding on surrounding gas and dust, their accretion disks shining with a light so brilliant it can be seen from the edge of the observable universe, outshining all the billions of stars in their host galaxy combined. These giants are not just cosmic oddities. They are fundamental architects of the universe. Their immense gravity shaped the formation of galaxies themselves. Their powerful emissions, when they are active, can regulate the birth of new stars across their galactic kingdoms, blowing away the cold gas needed for stellar nurseries. They are the gardeners of the cosmos, the silent thrones around which the stellar matter of the universe organized itself. From the ghost of a single dead star, we have traveled to the heart of galactic empires ruled by gravitational singularities of an almost incomprehensible scale. We have seen the commoners, and we have seen the kings. But this cosmic taxonomy presents a puzzle, a gap in the family tree. We have the stellar mass black holes ranging from a few to perhaps a few dozen solar masses, and we have the supermassive ones starting at 1 million and soaring to tens of billions of solar masses. But what about the ones in between? Where are the princelings and the dukes? The black holes with masses of hundreds or thousands or tens of thousands of suns. These are the so-called intermediate mass black holes, and they are the universe's missing link. For decades, they were purely theoretical, a frustrating blank space between two well-established populations. A single massive star collapsing cannot create something so large, and the processes that form supermassive giants in the hearts of galaxies do not seem to operate on this smaller, intermediate scale. So how could they form? One theory suggests they are born in the chaotic hearts of globular clusters, ancient, dense spheres packed with hundreds of thousands of old stars. In such a crowded environment, stars can collide and merge. Stellar mass black holes formed from the first generations of stars could sink to the center of the cluster and merge with each other, one by one, gradually building up their mass over billions of years. Another idea proposes that they are the leftover seeds of the first supermassive black holes, ancient relics from a time when galaxies were just beginning to form, which were ejected from their homes and now wander the cosmos in exile. Finding them has been an astronomical treasure hunt. They are too small to command the center of a major galaxy, and they don't have a constant companion star to feed on and reveal their presence. But slowly, hints have begun to emerge. Astronomers have seen stars being ripped apart with a violence that suggests a gravitational force greater than any stellar mass black hole could muster. They have detected mysterious off-center X-ray sources in other galaxies that flicker like the signature of a mid-sized black hole feeding. Each new clue is tantalizing, a piece of a puzzle that promises to rewrite our understanding of how these cosmic structures grow and evolve. The search for these middleweights reminds us that our cosmic census is far from complete, but our journey through the scales of size is not over. There is one more category to consider, one that takes us not just across space, but back to the dawn of time itself. To find this last class of black hole, we must travel to the very first moments of the universe. Imagine the cosmos, not as it is today, cold, dark, and mostly empty, but as it was in the first second of its existence. An unimaginably hot, dense, and turbulent sea of energy and fundamental particles. In this primordial soup, there were no stars to collapse. There were no galaxies to act as gravitational anchors. There was only the raw, chaotic energy of creation. Within this roiling inferno, it is theorized that the density was not perfectly uniform. In some regions, by pure chance, the quantum foam of spacetime may have fluctuated so wildly that pockets of energy and matter became compressed to impossible extremes. If a region became dense enough, it could collapse directly under its own gravity, forming a black hole without ever having been a star. These are primordial black holes. Because they were not born from stellar evolution, they are not bound by its rules. They could, in theory, come in any size. Some could have been enormous, the original seeds for the supermassive giants we see today. But others could have been astonishingly small. A primordial black hole with the mass of a large mountain could be smaller than a proton. One with the mass of our own moon would be no wider than a human hair. These microscopic relics of the Big Bang, if they exist, would be scattered throughout the universe today, silent and invisible witnesses to the first moments of creation. For decades, they remained a fascinating but untestable idea. But recently, they have been invoked as a possible solution to one of the greatest mysteries in all of science, the nature of dark matter. We know that about 85% of the matter in the universe is made of something we cannot see and do not understand. It does not interact with light, but its gravitational pull is what holds galaxies and galaxy clusters together. What if this missing matter isn't some exotic new particle, but a vast, unseen population of ancient tiny black holes forged in the fire of the Big Bang? The idea is staggering. The very structure of our universe, the cosmic web upon which galaxies are strung like pearls, might be held together by a swarm of microscopic gravitational points, each a remnant of the first instant of time. So we find that the term black hole does not describe a single thing. It is a vast and varied family of objects, a spectrum of gravitational beings that span the entire history and scale of the cosmos. We have journeyed from the ghost of a single star, no bigger than a city, to the supermassive anchors of galaxies that command the loyalty of billions of suns. We have sought the missing link in the middle, and we have peered back into the dawn of time to imagine black holes smaller than an atom. Each one, from the tiniest hypothetical relic to the most colossal galactic engine, is a point where the known laws of physics bend and break. Yet for all their differences in size, origin, and influence, they are united by one profound defining quality. They are invisible. The stellar mass waltzing with its companion, the supermassive giant holding a galaxy in its thrall, the primordial wanderer drifting between the stars, none can be seen directly. We have mapped their kingdoms, measured their masses, and witnessed their power, all without ever laying eyes on the objects themselves. They are ghosts in the machine of the cosmos, defined only by the void they leave behind. This raises a fundamental question. If they are perfect spheres of absence, set against the blackness of space, how can we be so confident they are there at all? How do we listen for the echoes from an abyss that consumes all sound, all light, all matter? How do we prove the existence of nothingness? Where the brilliant, violent light of the dying star once raged, there is now a profound and perfect silence. A new kind of object has settled into the fabric of the cosmos, an entity defined not by what it is, but by what it is not. It does not shine, it absorbs. It does not radiate, it consumes. It is a sphere of pure, featureless black, a patch of velvet night cut from the star-dusted tapestry of the galaxy. This is the ghost left behind, an object of pure gravity so dense that it has torn a hole in the very meaning of place and time. And yet, here lies the great challenge, the ultimate cosmic riddle. If a black hole is a perfect absence, a place from which no light can ever return, how can we possibly know it is there? How does humanity, confined to a small blue world, reach across the void and point to a patch of darkness and say with certainty, there is the abyss. We cannot see it. We cannot touch it. We can only hunt for its shadow, for the subtle and profound ways it imposes its will upon the universe around it. The search for a black hole is not a journey of observation, but of deduction. It is a grand detective story, and the cosmos itself is the scene of the crime. The culprit is invisible, but it always leaves clues. The first clue is perhaps the most elegant, written in the graceful language of motion. Imagine a quiet corner of the galaxy, seen through the patient eye of a telescope over many years, even decades. We are not looking for a sudden flash or a dramatic explosion. We are simply watching the stars, those ancient glittering constants, as they perform their slow celestial ballet. We focus on one star in particular. We measure its position tonight, and again next month, and again next year. A pattern begins to emerge. The star is not moving in a straight line, as an object adrift in space ought to, nor is it stationary. Instead, it is moving in a gentle, perfect arc. It is tracing a smooth elliptical path, as if waltzing with an unseen partner. Year after year, the evidence accumulates. The star completes its orbit, swinging around a central point where there is nothing. No shimmer of light, no companion star, no faint nebula, just empty black space. But the laws of gravity are as unforgiving as they are precise. For an object to be held in such a dance, it must be orbiting something else, something with immense gravitational pull. By measuring the star's speed and the size of its orbit, we can perform a simple cosmic calculation. We can weigh its invisible partner. At the heart of our own Milky Way galaxy, astronomers have performed this very act of celestial detective work for over a quarter of a century. They watched a star named S2 whip around a point of absolute blackness at astonishing speeds, at times reaching over 7,000 kilometers per second. Its orbit told a clear story. The invisible object at the center of that dance, the object we now call Sagittarius A, contains the mass of 4 million suns, all compressed into a space smaller than our solar system. There is no star, no cluster, no cloud of gas that could be so massive and yet so compact, so utterly dark. The only suspect that fits the evidence is a supermassive black hole. The dance of the star is the first echo from the abyss, a silent gravitational whisper that betrays the presence of the ghost. We do not see the dancer, but we see the precise, undeniable choreography it imposes on everything that dares to draw near. This gravitational fingerprint is subtle, a clue gathered through decades of patient watching. But sometimes the evidence is far more violent, far more visceral. A black hole does not only influence things from a distance, It is an active predator. When a cloud of interstellar gas or an unlucky star strays too close, it is not simply swallowed in an instant. Instead, it is subjected to a process of slow, spectacular destruction. Imagine that star again, not in a stable orbit, but on a doomed trajectory. As it approaches the event horizon, the black hole's gravity pulls more strongly on the side of the star that is closer than the side that is farther away. This difference in force, known as a tidal force, begins to stretch the star, pulling it apart like taffy. Great streams of stellar gas are ripped from its surface, not falling directly into the void, but being pulled into a frantic spiraling orbit around it. This material, stolen from a once mighty sun, forms a vast flat spinning structure, an accretion disk. And this is where the abyss, against its very nature, is forced to reveal itself. The matter in the disk does not spiral inward peacefully. It is a chaotic, high-speed traffic jam on a cosmic scale. Gas and dust particles, moving at nearly the speed of light, rub against each other. The friction is unimaginable, generating temperatures of millions, even hundreds of millions of degrees, far hotter than the core of any star. This superheated material does not simply glow. It screams. It unleashes a torrent of high-energy radiation, particularly X-rays and radio waves. While the black hole itself remains perfectly dark, the region just outside its event horizon becomes one of the brightest, most energetic places in the entire universe. Our X-ray telescopes orbiting high above the distorting veil of Earth's atmosphere can see these disks from across billions of light years. They appear as points of almost impossibly intense light, blazing with a fury that outshines entire galaxies. When we see such a beacon, we know we are not looking at a star. We are looking at a star's final moments. We are witnessing the death cry of matter as it spirals into oblivion. The light from an accretion disk is the second more terrible clue. It is the flash of the muzzle, the telltale sign of a cosmic predator at work. It is the proof that even in perfect darkness, there can be a blaze of terrible glory. But the story of the black hole's influence does not end with the inward spiral of matter. For some black holes, the ones that are spinning the cosmic crime scene, becomes even more extraordinary. The rotation of a black hole is not like the spinning of a planet. A spinning black hole drags the very fabric of space-time around, with it creating a swirling vortex of reality itself. This vortex, combined with the immense magnetic fields generated by the superheated accretion disk, creates a powerful cosmic engine. This engine does something astonishing. It takes a fraction of the matter spiraling inward moments before it is lost forever and redirects it. Instead of falling past the point of no return, this material is captured by the twisting magnetic field lines and funneled away from the disk. It is then accelerated to velocities approaching the speed of light and blasted outward in two colossal, tightly focused beams erupting from the black hole's north and south poles. These are known as relativistic jets. These are not mere plumes of gas. They are pillars of creation and destruction that can stretch for hundreds of thousands of light years, far larger than the galaxy that hosts them. They are so powerful, they can punch entirely out of their host galaxy, heating intergalactic gas and influencing the birth of new stars trillions of miles away. From our perspective on Earth, we cannot see the spinning black hole or its accretion disk. All we see are these two magnificent, impossibly long beams of light and energy, like the beams of a cosmic lighthouse. These jets are the third great clue. They are the unmistakable signature of a spinning, feeding supermassive black hole at the heart of a galaxy. To see the jet is to know with absolute certainty that at its source lies an engine of unimaginable power and density hidden within an event horizon. The abyss is not just consuming, it is broadcasting its presence across the cosmos, leaving trails of evidence vaster than we can properly comprehend. The dance of stars, the scream of gas, the lighthouses of the gods. These clues are powerful, convincing. They are all, however, indirect. They are the effects a black hole has on the light and matter that surround it. For decades, this was the best we could do. We had built a powerful circumstantial case, but we had never detected the culprit directly. We had never perceived the black hole itself, only the chaos it left in its wake. But that all changed in the 21st century. We finally found a way to listen for an echo from the abyss itself, a message written not in light or matter, but in the shape of space-time. Albert Einstein, in his theory of general relativity, told us that space and time are not a static backdrop. They form a dynamic, flexible fabric. Massive objects create dips and curves in this fabric, which is what we experience as gravity. He also predicted that when massive objects accelerate, they should create ripples in this fabric, much like a boat moving through water creates a wake. These ripples are gravitational waves. For a century, they were a purely theoretical idea. The waves from any normal event, like a planet orbiting a star, would be so infinitesimally small as to be utterly undetectable. To create a ripple large enough for us to feel across the universe, you would need an event of almost unimaginable violence and gravitational intensity. You would need the collision of two black holes. Imagine in the distant past, in a galaxy far, far away, two black holes born from the collapse of ancient, massive stars. They are locked in orbit, two perfect spheres of darkness circling one another in a silent, gravitational embrace. For millions of years they draw closer, their dance accelerating as they radiate away energy in the form of these subtle gravitational waves. In the final moments, they are moving at a significant fraction of the speed of light. They are no longer just warping the space-time around them. They are churning it into a storm. In the last fraction of a second, they merge. Two event horizons become one. The collision is an event of pure, raw gravity. It releases a burst of energy more powerful than the light of all the stars in the observable universe combined. But this energy is not light. It is a wave of pure space-time distortion, a tsunami of gravity that expands outward in all directions at the speed of light. This is the fourth and final clue, the sound of space-time itself, ringing like a bell. On Earth, we built instruments of incredible sensitivity to listen for this sound. The Laser Interferometer. Gravitational Wave Observatory, or LIGO, is not a telescope. It is more like a cosmic microphone. It consists of two tunnels, each several kilometers long, arranged in an L shape. A laser is sent down both arms and reflected back by mirrors. In the perfect silence of the cosmos, those two beams of light should return at the exact same time, canceling each other out. But if a gravitational wave passes through the Earth, it will stretch one arm of the detector while squeezing the other by a distance thousands of times smaller than the nucleus of an atom. This tiny, fleeting change is enough to knock the laser beams out of sync. For years, these instruments listened in silence. And then, on September 14, 2015, a signal arrived. A faint, rising tone that lasted for less than a second, a chirp. the unmistakable sound of two black holes 30 times the mass of our Sun merging into one over a billion light-years away. It was a message that had been traveling through the cosmos for 1.3 billion years. It was not the light from a dying star or the X-rays from a violent disk. It was the direct, unambiguous tremor from the event itself. We had not seen the abyss, but we had finally truly felt its presence. The case is now closed. The invisible culprit stands, revealed not by a single piece of evidence, but by a wealth of clues that all point to the same conclusion. From the patient observation of a star's lonely dance, to the violent, brilliant scream of an accretion disk, to the colossal jets that pierce the heavens, and finally to the fundamental ringing of reality itself. The black hole has left its fingerprints everywhere. We have found our ghost in the cosmic machine. We have mapped its shadow, heard its influence, and felt its tremors. The portrait drawn by the grand laws of gravity and motion appears complete. The abyss is silent, absolute, and final. Or is it? We have built this understanding by looking at the universe on its grandest scales, the scales of stars and galaxies and space-time itself. But what happens if we change our perspective? What happens if we lean in close to the edge of that perfect darkness and listen, not with the grand instruments of astronomy, but with the subtle, paradoxical rules of a different kind of physics, the physics of the very small? When we bring the strange logic of the quantum world to the event horizon, the silence is broken. We begin to hear a faint, almost impossible whisper. The abyss, it seems, is not entirely black after all. For an eternity, or what feels like one in the silent theater of space, our object of pure gravity has been defined by its finality. It is an endpoint, a destination from which there is no return, a period at the end of a cosmic sentence. General relativity, the grand and elegant theory of gravity that predicted its existence, paints a picture of stark classical certainty. An edge, a point of no escape, and beyond it, an inescapable singularity. The laws are absolute, the geometry, clean, the outcome inevitable. But the universe, we have learned, does not always speak in the language of absolutes. Below the grand sweeping narrative of space-time, there is another story being told, a story of shimmering uncertainty, of fleeting possibilities of a world that is fundamentally fuzzy, chaotic, and alive with potential. This is the language of quantum mechanics, and when we bring its whisper to the silent edge of the black hole, the silence is broken, and the absolute begins to dissolve. To understand this deep riddle, we must first adjust our vision. We must look at what appears to be nothing at all. Let us zoom in closer and closer on a patch of what we call empty space, far from any star or planet. In the classical view, this is a void, a perfect vacuum, cold and inert. But through the quantum lens, this emptiness is a seething, effervescent cauldron of activity. It is a foam of potential, a constant flux where pairs of particles, one of matter, one of antimatter, spontaneously burst into existence from the underlying energy field of the universe. They are called virtual particles because their lives are impossibly brief. They are born from a borrowed sliver of energy, and to repay this cosmic debt, they must find each other and annihilate almost instantly, vanishing back into the nothingness from which they came. They exist for a time so short it defies our intuition, a fleeting flicker on the margins of reality. This is not a theory, but a measured and confirmed reality of our universe. The vacuum is not empty. It is humming with the ghost-like echoes of creation and destruction, a constant subtle fizz of being and non-being. Now let us carry this vision back to the edge of our black hole, to the silent, perfect sphere of the event horizon. Here this quantum dance becomes a high-stakes drama. Imagine one such pair of virtual particles, an electron and its antimatter twin, a positron, flickering into existence at the very precipice of the abyss. In the vast emptiness of space, they would have a simple fate to find each other in the next instant and disappear. But here, at the gravitational cliff edge, their destiny can be torn apart. The black hole's immense gravity exerts a tidal force of unimaginable power even on this microscopic scale. It is possible for one of the pair to be captured, to fall across the event horizon, while its partner escapes. Let us imagine the positron, the antimatter particle, falls in. The electron, its twin, is now stranded, left alone just outside the horizon. It can no longer annihilate with its partner to repay the energy loan that created them both. It is an orphan of the quantum foam. To an observer far away, this lone electron, now free, appears as a real particle radiating away from the black hole. It has escaped the void, but the universe keeps perfect accounts. Energy cannot simply be created from nothing. The escaped electron now carries real positive energy out into the cosmos. That energy had to come from somewhere. The particle that fell into the black hole provides the answer in a way that bends our understanding of reality. To balance the books, quantum field theory suggests that the particle falling into the black hole must be considered to have negative energy relative to an observer in the outside universe. When this negative energy particle is consumed by the black hole, it subtracts from the black hole's total mass energy. It is as if the black hole has paid the debt for the escaped particle's existence. A single particle carries an infinitesimal amount of mass. The loss is unimaginably small, far less than the mass of a single grain of sand. But this process is not a singular event. It happens constantly all over the vast surface of the event horizon. Particle by particle, whisper by whisper, the black hole is losing mass. It is radiating. This is the profound discovery of Stephen Hawking, that black holes are not perfectly black after all. They have a faint glow, a thermal signature born from the quantum chaos at their edge. They shine not with the light of a fire, but with the ghostly light of particles liberated from the void. And in this faint glow lies a startling prophecy. If a black hole radiates, it is losing mass. And if it loses mass, it must shrink. The process is fantastically slow. For a black hole, the mass of our sun, the time it would take to radiate away completely, is a number so large it dwarfs the current age of the universe. It is a 1 followed by 67 zeros, an eternity beyond all human conception. For the supermassive giants at the hearts of galaxies, the timescale is even more staggering. They will likely be the very last objects to remain in a cold, dark, and empty universe long after the last stars have faded. They will persist as lonely cosmic embers, slowly, patiently whispering themselves out of existence over trillions upon trillions of years. This slow evaporation, this Hawking radiation, transforms the black hole from an eternal prison into a finite mortal object. It has a lifespan. It will eventually die. And in its death we find the greatest paradox of all. Physics at its most fundamental level has a sacred rule: information is never lost. The state of any system, the precise properties and arrangement of all its constituent parts, is preserved. You can burn a piece of paper. To our eyes, the information in the ink and fibers is gone, turned to ash and smoke. But in principle, if you could capture every single particle of smoke, every photon of heat, every atom of ash, and trace its trajectory, you could reconstruct the original message. The information is not destroyed. It is merely scrambled, redistributed in a way that is incredibly difficult to track. This principle of information conservation is a bedrock of quantum mechanics. It ensures that the past is uniquely linked to the present and the present to the future. But the black hole presents a terrifying challenge to this rule. Imagine we throw an encyclopedia into a black hole. The encyclopedia contains a vast amount of information in the specific arrangement of its ink molecules, the sequence of its letters, the stories and facts encoded within. This information crosses the event horizon and, according to relativity, is lost to the outside universe, forever crushed into the singularity. For a long time, this was strange, but not a true paradox. One could simply imagine that the information was still there, locked away inside the black hole's impenetrable vault. But Hawking's discovery changes everything. If the black hole slowly evaporates, what happens to the information it swallowed? The radiation it emits, this Hawking radiation, appears to be purely thermal. It is random generic heat. Its properties seem to depend only on the black hole's mass charge and spin, not on the unique contents of the encyclopedia or the star or the spaceship that fell inside it. So when the black hole finally vanishes in a final quiet puff of radiation, the information about everything it ever consumed seems to have vanished with it, utterly and completely. This is the information paradox. It creates a deep and troubling chasm between our two great theories of the universe. General relativity creates an object that appears to destroy information, while quantum mechanics insists that such destruction is impossible. It is not just an academic puzzle. It strikes at the very heart of our understanding of cause and effect of time and of the nature of reality itself. Does the universe keep a perfect memory of itself, or can its history be erased? The search for a resolution has pushed physicists to the very edge of imagination. One of the most elegant and profound ideas to emerge is known as the holographic principle. It suggests something that sounds like science fiction, that all the information about a volume of space can be described by the physics on its boundary. The universe, in this view, might be like a hologram, a three-dimensional image projected from a two-dimensional surface. Applying this to a black hole, the principle suggests that the information about everything that has fallen into its three-dimensional interior is not actually lost inside. Instead, it is somehow encoded, scrambled, and imprinted upon the two-dimensional surface of its event horizon. The event horizon itself acts as the holographic plate. The information is not gone, just stored in a radically different format, like the data for a complex simulation stored on a vast spherical hard drive. As the black hole evaporates particle by particle, this incredibly complex information is not destroyed. It is subtly and painstakingly leaked back out, imprinted in the delicate quantum correlations between the outgoing particles of Hawking radiation. The escaping glow is not as random as it first appears. It is an exquisitely scrambled message, a cosmic phoenix carrying the ashes of the encyclopedia, the star, and everything else the black hole ever consumed. To us, it might look like noise, but hidden within its quantum structure is every last bit of the information that we thought was lost forever. This idea is far from proven, but it is a beautiful and compelling potential solution. It suggests that the universe is more clever, more interconnected, and stranger than we can easily comprehend. It tells us that the boundary of a black hole is not just an edge of no return, but perhaps a repository of memory, a screen upon which the story of everything that has been lost is written in the language of quantum physics. We have stood at the precipice, gazing at the subtle quantum fire that licks at the edges of space-time. We have seen that this object of perfect darkness is not an eternal monolith, but a shimmering, evaporating ghost whispering the secrets of its past back into the void over timescales that beggar belief. The paradoxes found at its boundary are not failures of our science, but invitations, gateways to a deeper understanding of space-time and information. But all of our contemplation, all of these thought experiments, have kept us safely on this side of the line. We have studied the horizon, but we have not crossed it. The quantum riddle tells us what happens at the edge over eons, but it does not tell us what happens in the moment of passage. What is the nature of the fall? What happens to time, to space, to the very fabric of reality for an object that takes the final, irretrievable step? Having wrestled with the ghost on the boundary, we must now turn our gaze inward and take a speculative journey into the maelstrom itself. For an eternity, or what feels like one in the silent theater of space, our object of pure gravity has been defined by its finality. It is an endpoint, a destination from which there is no return, a period at the end of a cosmic sentence. General relativity, the grand and elegant theory of gravity that predicted its existence, paints a picture of stark classical certainty. An edge, a point of no escape, and beyond it, an inescapable singularity. The laws are absolute, the geometry clean, the outcome foretold. But what if we were to not just observe, but to participate? What if we could follow the light, follow gravity itself, down into the final quiet? Let us suspend our fear and embark on a journey of pure imagination, a thought experiment guided by the strange and beautiful mathematics that describes this place. We will not fall. We will descend with purpose, with a quiet curiosity to witness the unraveling of the world we know. As we approach, the universe behind us begins to warp. The familiar tapestry of stars, once a serene backdrop, is now pulled and distorted as if viewed through a cosmic lens of impossible power. Starlight bends around the unseen sphere, creating a shimmering halo, an Einstein ring of ghostly duplicated constellations. The black circle ahead is not an absence of light, but an absence of space itself, or rather a place where space has been given a new, terrifying, and ultimate direction, downward. The closer we drift, the more the sky contorts. The entire celestial sphere compresses into a smaller and smaller window, a bright, swirling porthole of the out there. And in this final vision of home time, itself begins to stretch. For an observer watching us from a safe distance, our approach would slow to a crawl. Our light would redden its waves, stretched by the immense gravity, shifting from blue to red to infrared until we fade from their view entirely, a frozen ghost image painted forever on the edge of the abyss. But for us, time flows as it always has. It is the universe itself that seems to be accelerating, its entire future history flashing before our eyes in that shrinking window of light. We witness stars being born and dying in moments, galaxies colliding in a silent, beautiful ballet. We are crossing a temporal ocean, watching eons pass like seconds. Here at the threshold, we must make a choice. Not all black holes are created equal. If this were a smaller one, born from the collapse of a single massive star, our journey would end before it truly began. The tidal forces here would be immense. Gravity's pull on the part of us closer to the center would be exponentially stronger than on the part further away. We would be stretched, elongated, pulled apart atom by atom in a process so fundamental it has earned the unsettlingly whimsical name spaghettification. It is the ultimate deconstruction, a return to a stream of fundamental particles, a line drawn back into the source code of matter. But our journey is a gentler one. We have chosen a different path, a descent into a supermassive black hole, the kind that slumbers at the heart of a galaxy like our own Milky Way. Here, millions or billions of times the mass of our Sun, the curvature of space-time at the event horizon is far more gradual. The edge is so vast that the tidal forces are for a time survivable. The stretching is negligible. For us, the crossing of this boundary, this fabled point of no return, is an event of profound subtlety. There is no wall, no membrane, no sudden jolt. It is a quiet, seamless transition. One moment escape is in theory possible. The next moment, it is not. The laws of physics have not been broken. They have simply revealed a new, inviolable clause in their contract with reality. We have crossed. We are inside the maelstrom. The bright window to the outer universe is now gone. We are enveloped in a perfect, featureless darkness. But it is not the empty darkness of interstellar space. It is a charged directional darkness, a space that has an inherent and irresistible flow. And here, the most profound transformation, occurs a change so deep it rewrites the very grammar of existence. The roles of space and time have been exchanged. Consider your life a journey through time. You can move freely through space, left or right forward, or back up or down. You have 3 dimensions of freedom, but you have no such freedom in time. You are carried relentlessly forward from the past through the present into the future. Time is a one-way street, a river on which you are an unwilling passenger. You cannot stop it. You cannot reverse it. You can only move toward tomorrow. Inside the event horizon, this reality is inverted. The 3 dimensions of space, up, down, left, right, are no longer directions you can choose to travel. They have all collapsed into a single, inescapable direction inward toward the center. Just as you are always pulled toward the future in the outside world here, you are pulled inexorably toward the singularity. You can no more stop your descent than you can stop the passage of time itself. All paths, all trajectories, every possible movement now leads to the same destination. The future is no longer a time, it is a place. And what of time? Time has become the new dimension of freedom. Just as you could once move around in space, you now have a strange, limited mobility in the temporal dimension. But it is a freedom without a purpose, a freedom that leads nowhere. The river has become a still, dark lake, and you are adrift. There is no forward in the temporal sense anymore, only inward in the spatial one. The very concepts of cause and effect, of before and after, begin to lose their meaning. If all paths lead to the same endpoint, does the path taken matter? If the future is a physical place you are falling toward, has it not, in a sense, already happened? the pressure grows. Not a physical pressure on our imagined form, but a conceptual pressure on reality itself. The fabric of space-time is being crushed. The darkness ahead seems to thicken to take on a quality of infinite density. We are approaching the heart of the matter, the place where the story of this collapsed star, this cloud of gas, this captured light, reaches its final incomprehensible conclusion. We are approaching the singularity. Physics as we know it has no words for this place. Our most powerful theories, general relativity and quantum mechanics, which together describe the universe with breathtaking accuracy, break down here. Their equations return infinities. Their logic dissolves into paradox. It is the point where our understanding ceases. It is a boundary not of the universe, but of our knowledge. In our guided journey, what do we perceive? Perhaps it is not a point at all. Some theories suggest it is a ring, a vortex of space-time so fiercely twisted that it defies geometry. Others speculate that it is a quantum foam, a roiling sea of possibilities where space and time dissolve into a probabilistic haze. Perhaps it is a gateway, a wormhole to another universe, a place where the laws of physics are reset, rebooted into a new creation. We do not know. We cannot know. But in the classical picture painted by relativity, the singularity is the end. It is a moment in time, not a place in space. It is the final future for everything that has crossed the event horizon. As we approach our own structure, the imagined vessel of our consciousness begins to lose its integrity. The distinction between self and other, between particle and wave, between energy and matter, dissolves. The fundamental forces of nature, once distinct, may merge back into a single unified state, the one from which the entire universe burst forth in the Big Bang. We are witnessing a return to the origin, a universe in reverse. Matter is compressed to a state of infinite density, temperature, and curvature. Time itself comes to a halt. It is not that we run out of time. It is that the dimension of time ceases to exist. There is no after the singularity. There can be no after, because the very framework that allows for an after has been dismantled. It is the ultimate silence, the final note in a symphony of gravity, a full stop at the end of all things. Here in this conceptual space beyond existence, we are no longer an observer. We have merged with the object of our study. The information that once made us, our memories, our atoms. Our light is now part of the singularity itself. We are one with the crushed star, the captured photons, the immense silent gravity. We have reached the bottom of the well, and yet, even here in this theoretical abyss of absolute finality, a question hums in the silence. Is an end ever truly just an end? In our universe, energy is never created or destroyed, only transformed. Information, some physicists argue, can never be truly lost. So what has become of all that has fallen into this cosmic furnace? The lives of countless stars, the dust of ancient nebulae, the light from distant galaxies, has it all been simply erased from the cosmic ledger? Or has it been replanted? Perhaps this act of utter destruction is not a conclusion, but a form of profound alchemy. Perhaps the crushing force of the singularity, this endpoint of all known physics, is also a crucible, a place where the raw material of reality is broken down so completely that it can be used to forge something entirely new. We think of the black hole as a tomb, a celestial predator that consumes and ends. But what if that is only one half of the story? What if by ending old worlds, these gravitational titans are preparing the ground for new ones? What if this maelstrom is not a grave but a seed? This ending, this beautiful, terrifying, absolute end, might just be the dark, fertile soil from which new creations can grow. For an eternity, or what feels like one in the silent theater of space, our object of pure gravity has been defined by its finality. It is an endpoint, a destination from which there is no return, a period at the end of a cosmic sentence. General relativity, the grand and elegant theory of gravity that predicted its existence, paints a picture of stark classical certainty. An edge, a point of no escape, and beyond it, an inescapable singularity. The laws are absolute, the geometry, clean, the outcome preordained. It is the ultimate consumer, the final stop. But what if this picture, so clear and so terrifying in its simplicity, is profoundly incomplete? What if the end is also a beginning? What if the period is also a seed? The universe, in its deep and patient wisdom, rarely deals in absolutes. It prefers cycles, transformation, and a delicate, often violent balance. The story of the black hole, when we pull our gaze back from the precipice of its event horizon and look at the vast cosmic landscape it inhabits, transforms. The image of the silent, waiting void begins to dissolve, replaced by something far more dynamic, more intricate, and impossibly more alive. The destroyer becomes an architect, the predator a gardener. Imagine a vast, dark field stretching for light years. It is filled with a thin, cold mist of hydrogen and helium, the primordial elements left over from the dawn of time. This is the raw material of creation, but it is diffuse, directionless, lacking a center of gravity to gather it into something more. It is a garden without a gardener soil, without a seed. Now, into this field place, a single impossibly dense point of mass, a supermassive black hole. Its gravity does not just pull, it organizes. Like invisible hands shaping clay, its influence reaches out, coaxing the scattered dust and gas into a gentle, swirling dance. The mist begins to coalesce, to spin, forming a vast rotating disk. This is the birth of a galactic protodisk, the foundation of a future city of stars. The black hole sits at the very heart of this nascent structure, not as a passive object, but as its anchor. The entire swirling symphony of matter, which will one day become billions of stars and planets, is orchestrated around this central point. The grand spiral arms of a galaxy like our own Milky Way are not mere accidents of celestial aesthetics. They are density waves, gravitational ripples in a cosmic pond, and their stability and form are intimately tied to the mass of the supermassive black hole reigning silently at their center. Without Sagittarius A, our own galaxy's quiet giant, the Milky Way might never have settled into its beautiful pinwheel shape. The Sun, our solar system, and our very existence might have been flung out into the desolate cold of intergalactic space, or never have had a stable environment in which to form at all. This is the first act of the cosmic gardener to prepare the soil. It provides the fundamental structure, the gravitational bedrock, upon which everything else can be built. It is the silent, patient force that turns a chaotic cloud into a coherent, organized system, a home for future generations of stars. It gathers the potential of the universe and gives it a place to flourish. But a garden requires more than just good soil. It needs tending. It needs a careful balance of destruction and creation, of pruning and seeding. A garden left entirely to its own devices can become overgrown, choking itself out. A galaxy too can suffer from its own unchecked growth. If all the gas in a young galaxy were to collapse into stars at once, it would be a brief, spectacular blaze of glory, followed by an eternity of darkness. The galaxy would burn through its fuel in a cosmic flash, leaving no raw material for future star birth. The garden would bloom once magnificently, and then die forever. Here, the black hole reveals its second, more active role. It is not just a passive anchor, it is a regulator, a dynamic engine at the heart of the galaxy. As gas and stars spiral inwards, they don't simply fall across the event horizon. They form a swirling, superheated accretion disk around the black hole, a cosmic traffic jam of matter, moving at nearly the speed of light. The friction and magnetic forces in this disk heat the material to millions of degrees, causing it to shine with an intensity that can outshine all the billions of stars in its host galaxy combined. This is a quasar, a quasi-stellar object, the blazing signature of a feeding black hole. And from the poles of this incandescent disk, the black hole unleashes something extraordinary: colossal jets of energy and particles fired out into the cosmos at relativistic speeds. These jets can be unimaginably vast, stretching for hundreds of thousands of light years far beyond the visible edge of the galaxy itself. They are the gardener's tools, and they perform a dual function of magnificent importance. In one sense, these jets are a destructive force. They are a form of what astronomers call galactic feedback. As they tear through the galaxy, they act like a powerful cosmic wind, blowing away huge clouds of gas. They heat up the interstellar medium, making it too hot and too diffuse to collapse and form new stars. This is the act of pruning. The black hole is actively preventing runaway star formation. It's thinning the canopy, ensuring that the galaxy doesn't use up all its resources at once. It's a harsh, violent process, but it is essential for the long-term health of the galactic ecosystem. It preserves the reservoir of gas, allowing for a slow, steady simmer of star birth that can last for billions of years rather than a single self-extinguishing explosion. But the gardener does not only prune, the gardener also seeds. The very same jets that blow gas away in one region can have the opposite effect in another. As the shock wave from these powerful outflows expands through a galactic arm, it can slam into a cool, dense cloud of molecular gas. This sudden compression can be the exact trigger needed to kickstart gravitational collapse. The shock wave acts like a hand squeezing a sponge, forcing the gas together until its own gravity takes over and a new generation of stars ignites. So the black hole, in a single powerful act, both halts creation and instigates it. It is a force of cosmic balance, ensuring the garden is neither barren nor overgrown, but remains a vibrant, evolving place of birth and renewal. It is the galaxy's own self-regulating heart pumping energy out to maintain a delicate equilibrium that makes long-term evolution and perhaps life possible. The work of the gardener, however, goes even deeper than shaping the structure and regulating the growth of the garden. It is also about enriching the soil itself, ensuring that future generations have the ingredients they need, not just to exist, but to create complexity. The early universe was made almost entirely of hydrogen and helium, the two lightest elements. Every other element on the periodic table, the carbon in our cells, the oxygen we breathe, the iron in our blood, the silicon in the rocks beneath our feet, was forged in the hearts of stars and blasted out into the cosmos when those stars died. These heavy elements are the seeds of life, and the building blocks of rocky planets. But getting them from the stars, where they were made, to new star-forming regions across the vastness of a galaxy, is not a simple matter. They need to be mixed, churned, and distributed. Here again, the black hole plays a crucial, if indirect, role. The cataclysmic events associated with black holes, the powerful jets from a quasar, the gravitational chaos of two galaxies merging their central black holes, spiraling towards each other, are among the most effective mechanisms for stirring the galactic pot. Imagine a supernova explodes, scattering a cloud of freshly minted gold, platinum, and carbon into its local neighborhood. Without a larger force, that cloud might stay relatively contained. But the powerful outflows from the central black hole can catch this enriched material and hurl it across tens of thousands of light years, seeding distant barren clouds of hydrogen with the elements necessary for new, more complex solar systems to form. The gravitational dance of a black hole merger can fling entire star systems and the enriched gas between them into new orbits, mixing the galaxy's contents like a cosmic baker kneading dough. In this sense, the black hole is not just a gardener, but an alchemist's assistant. It takes the base elements of the universe and ensures the precious life-giving ingredients forged in stellar fires are not lost or isolated, but are spread far and wide. The journey of a single carbon atom from the core of a long-dead star to becoming part of a living organism on a small, rocky planet is a journey that may well have been directed by the ancient, powerful breath of a supermassive black hole. The destroyer is the distributor. The taker is the ultimate giver, participating in a grand cycle of cosmic recycling that makes our own existence possible. And so the classical image of the destroyer recedes, replaced by something far more nuanced and beautiful. We see the cosmic gardener, the architect, the regulator. We see its handiwork in the grand spiral of our own galaxy, in the steady rate of new stars being born in the very elements that make us who we are. This understanding, born from observation, from computer simulation, and from the patient collection of light from the far corners of the cosmos, gives us a profound sense of place. The black hole is not an anomaly to be feared, but a fundamental and creative part of the universe's life cycle. It is as essential to the cosmos as forest fires are to the health of a forest, a destructive force that clears the way for new growth, returns nutrients to the soil, and maintains the vitality of the whole. But this new picture, as beautiful and complete as it feels, is painted with a very broad brush. It describes the black hole's effect on the world around it, its role in the grand ecosystem. When we lean closer, however, when we try to examine the gardener's hands, the nature of its tools, the physics of gravity at its most extreme, the details blur into an impenetrable fog. The elegant laws that describe its galactic influence with such precision begin to fray and tear when we ask them to describe the event horizon itself, or the impossible point of the singularity at its heart. For all we have learned about what black holes do for the universe, the more fundamental question of what they are, at their core, pulls us back into the darkness. We have described the shadow, but not the object casting it. We have mapped the garden, but the gardener remains a mystery. We stand at the edge of a cosmic landscape we can finally begin to comprehend, but its most fundamental principles, the very laws that govern its heart, remain shrouded in a mist. We are only just beginning to learn how to navigate. We have reached the limits of our classical descriptions, and to go further, we must venture into a realm where our most cherished ideas about space-time and reality itself break down. We have reached the edge of knowledge. For an eternity, or what feels like one in the silent theater of space, our object of pure gravity has been defined by its finality. It is an endpoint, a destination from which there is no return, a period at the end of a cosmic sentence. General relativity, the grand and elegant theory of gravity that predicted its existence, paints a picture of stark classical certainty. An edge, a point of no escape, and beyond it, an inescapable singularity. The laws are absolute, the geometry clean, the outcome inevitable. But this beautiful, terrifying clarity begins to tremble at the very heart of the abyss. As we draw closer to that central point, our most trusted map, the map of space-time drawn by Einstein, leads us to a place where the landscape dissolves into infinity, infinite density, infinite curvature. The mathematics, so elegant and precise everywhere else, simply breaks. It yields an answer of error. And in the language of physics, an infinity is not an answer. It is a question. It is a signpost glowing in the dark that reads, "Our knowledge ends here." This is the great humbling frontier. For decades, the singularity was accepted as a paradox. We had to live with a mathematical artifact where our theories were known to fail. We held two monumental ideas in our hands: general relativity, the law of the very large governing planets, stars, and galaxies with perfect flowing curves, and quantum mechanics, the law of the very small governing atoms and particles with jittery, uncertain quantized steps. In the cosmos at large, these two rule their own domains, rarely interacting. But in the heart of a black hole, they are forced into the same infinitesimal space. Gravity becomes so strong that it acts on a quantum scale. And here, in this crucible of extremes, our two pillars of understanding refuse to speak the same language. The smooth fabric of space-time envisioned by Einstein meets the pixelated probabilistic world of the quantum, and the conversation falls silent. This silence is where the true journey begins. It is an invitation to listen more closely, to imagine more freely, and to ask a more profound question: what truly lies at the center? Is the singularity really an infinitely dense point? Or is that just the simplest answer our current equations can give us? Science, in its deepest and most honest form, is not a collection of settled facts, but an ongoing dialogue with mystery. And the heart of a black hole is where that mystery speaks most eloquently. It asks us to abandon the comfort of our old maps and to consider that the destination may be nothing like what we expected. One of the first whispers of a new possibility came not from changing the laws, but from looking at them more closely. The simplest black hole, a non-rotating sphere of pure mass, is what gives us the classic point-like singularity. But almost nothing in the universe is perfectly still. Stars spin, galaxies spin. The conservation of angular momentum ensures that whatever collapses to form a black hole carries its spin with it. When a star spins, it bulges at its equator. So what happens when a spinning star collapses? The mathematics worked out by the physicist Roy Kerr reveals something extraordinary. The singularity is no longer a point. Instead, the relentless crush of gravity, counteracted by the furious centrifugal force of its own spin, is smeared out into a ring. An infinitely thin, infinitely dense circle spinning at a tremendous rate. Imagine falling towards this object. You would not be drawn to a single central point of doom. Instead, you would be drawn towards the plane of this spinning ring. If you were to pass through the center of the ring itself, through the hole in the cosmic donut, the equations suggest something almost unbelievable. Space-time within the ring is so warped that it turns back on itself. It becomes a gateway. This is the first hint that the black hole is not just an end, but perhaps a passage. The ring singularity acts as a theoretical bridge, a portal where the laws of our universe are so contorted that they might connect to somewhere else, or when else. The idea is staggering, and it comes directly from the equations of general relativity we thought we knew so well. It suggests that the finality of the black hole was only part of the story, the simplest version of a far more complex and bizarre entity. The universe, it seems, has more imagination than we do. But even this ring of infinite density is still a singularity. It is still a place where our physics breaks down. Quantum mechanics still warns us that nature abhors an infinity. And so, a more radical idea began to take shape, born from the most ambitious and strangest of our modern theories, string theory. String theory proposes a simple yet revolutionary idea that at the most fundamental level, the particles we see, electrons, photons, quarks, are not points. They are unimaginably tiny, vibrating loops of energy, like the strings on a cosmic violin. The different ways these strings vibrate give us the different particles, just as different vibrations of a violin string give us different musical notes. The universe, in this view, is a grand symphony of these vibrating strings. So what does a black hole look like through the eyes of string theory? The answer dismantles the classical picture entirely. As a star collapses, it doesn't form a region of empty space surrounding an infinitely dense point. Instead, as the matter and energy are crushed together, the strings that compose them become tangled, overlapping, and vibrating in a complex, chaotic dance. They do not collapse to a singularity. Instead, they form a massive, densely packed ball of strings, a fuzzball. In this view, the black hole has no empty interior. The event horizon is not a smooth, featureless boundary in space, but the very surface of this tangled ball of energy. It is a fuzzy, shimmering sphere, and everything that has ever fallen in every star, every particle, every photon, is not lost or destroyed. Its information is preserved, woven into the complex vibrations of the strings on this surface. The singularity, the point of infinite madness, simply vanishes from the theory. It is replaced by a physical object, albeit one made of the most fundamental stuff of reality. The information paradox that plagued physics for decades, the puzzle of where information goes when it falls into a black hole, is elegantly solved. It isn't gone. It's just been transcribed into a new language, the language of vibrating strings, and stored on the surface of this cosmic fuzzball. This idea transforms the black hole from a celestial monster into a celestial archive. It becomes the most densely packed hard drive in the universe, a place where the story of everything it has ever consumed is written in the subtlest of cosmic vibrations. The clean, terrifying geometry of Einstein gives way to a messy, complex, and strangely more organic reality. It is a profound shift in perspective, suggesting that even in the most extreme places, the universe prefers complexity and information over oblivion. And yet, the spirit of Einstein's geometry still inspires us to ask about passages. If a black hole is an entrance, is there an exit? This question leads us to one of the most famous and tantalizing concepts in all of physics, the wormhole. The formal name is an Einstein-Rosen bridge, and it emerged from the mathematics of general relativity as a beautiful symmetric solution. Imagine space-time as a two-dimensional sheet of paper. A massive object, like a star, creates a dimple in it. A black hole creates a deep, funnel-like well, a puncture from which nothing can escape. But the equations allowed for another possibility. What if that funnel connected to another inverted funnel somewhere else on the sheet of paper? You would have a tunnel, a shortcut, through the fabric of space-time itself. This is a wormhole. One mouth would be a black hole, a place you can only enter. The other mouth would be its theoretical opposite, a white hole, a place you can only exit. A white hole is a perfect time reversal of a black hole. It is a region of space-time that erupts with matter and energy, but which nothing can ever enter from the outside. It is a cosmic fountain, a wellspring of creation. For a long time, white holes were dismissed as a mathematical curiosity. They seem to violate the second law of thermodynamics, which states that entropy or disorder must always increase. A white hole would be a source of immense order, seemingly appearing from nowhere. We have never seen one, nor do we have any evidence that they exist. But the idea persists, a ghostly twin to the black hole in our theories. Some speculative cosmologists wonder if the Big Bang itself could be thought of as a kind of white hole event, the ultimate eruption of energy and matter from a single point. Could it be that at the heart of every black hole, the crushing pressure of the singularity is so great that it rebounds, punching through to another place or time and emerging as a white hole? Could our universe be one of many connected by these cosmic bridges, with black holes acting as the seeds for new universes, each one blooming from the collapse of a star in a parent cosmos? This is the very edge of speculation, a place where physics borders on metaphysics. The wormholes described by the original equations are thought to be incredibly unstable. They would snap shut in an instant long before even a single photon could pass through. To hold one open would require a form of exotic matter with negative energy or negative pressure, a substance we are not even sure can exist. And yet, the possibility remains a haunting and beautiful one. It suggests that space-time is not just a stage on which the cosmic drama unfolds, but an actor in its own right, capable of folding, tearing, and reconnecting in ways that defy our everyday intuition. The universe might be riddled with these hidden pathways, these secret corridors, connecting distant stars, distant galaxies, and perhaps even distant realities. The black hole, then, is not just a tomb for light, but a locked door. And while we do not yet have the key, the mere existence of the door changes everything. It tells us that the house we live in, our universe, may have rooms we have not yet discovered. Here, at this precipice of knowledge, we are left not with answers, but with a richer, more profound set of questions. Is the heart of a black hole an infinitely sharp point, a spinning ring, or a fuzzy ball of cosmic strings? Is it an end, a final resting place for matter and energy? Or is it a beginning, a bridge, a seed for a new creation? Each theory is a different attempt to complete the story, to fill in the blank page that the singularity represents. The beauty of this moment in science is the humility it demands. We are explorers who have reached the edge of the known map. Ahead of us lies an ocean of uncertainty. We can see the shapes of distant continents in the mist, fuzzballs, wormholes, new universes, but we cannot yet be sure if they are real or mere mirages. All we can do is build better ships, craft better instruments, and listen more intently to the subtle whispers of the cosmos. We must learn to be comfortable with not knowing, to see the unknown not as a void, but as a space of infinite potential. The black hole, once a symbol of absolute certainty and finality, has become the greatest teacher of cosmic humility. It has shown us that the most profound truths are not found in the answers we have, but in the courage to keep asking the questions that seem impossible to answer. It is a conversation between the finite human mind and the infinite universe. And in this conversation, we have journeyed from the certainty of a falling star to the deep quantum ambiguity at the heart of space-time. We have peered into the abyss and found not just an end, but a tapestry of astonishing possibilities. And so we stand at this precipice of understanding, staring into the heart of what we do not know. We have traveled billions of light years across cosmic voids and through spiraling galaxies, all to arrive at a question mark. But perhaps the greatest mystery is not what lies within the black hole, but what stirs within us as we look upon it. The awe, the curiosity, the profound and unshakable sense of connection to a universe that built us from stardust, and now through our minds begins to question its own deepest secrets. In this vast, silent darkness, a flicker of human consciousness has posed a question to the eternal night. Now it is time to turn our gaze away from the edge to carry that question with us as we journey back from the darkness, returning to the light. For an eternity, or what feels like one in the silent theater of space, our object of pure gravity has been defined by its finality. It is an endpoint, a destination from which there is no return, a period at the end of a cosmic sentence. General relativity, the grand and elegant theory of gravity that predicted its existence, paints a picture of stark classical certainty. An edge, a point of no escape, and beyond it, an inescapable singularity. The laws are absolute, the geometry, clean, the outcome foretold. But our journey was never one of matter. It was a journey of consciousness, of attention. And unlike a particle of dust or a photon of light, our awareness is not bound by the one-way street of space-time. And so we can do what nothing else can. We can turn back. We can return. Let us pull our focus away now, slowly, gently. From the sharp, perfect black circle of the event horizon, we begin our retreat. The gravitational lensing that bent the starlight into a swirling halo begins to unwind. The distorted tapestry of the cosmos straightens itself out. That feeling of an inexorable pull of a universe tilted downhill towards a single point begins to fade. It is replaced by the serene, quiet coasting of deep space. The silence is different out here. Near the black hole, it was a silence of absence of consumption. Here it is a silence of potential, of distance, of peace. The great cosmic engine recedes behind us, becoming once again just a single, impossibly dark point among a billion points of light. We have stood at the edge of the abyss, looked into the heart of a cosmic mystery, and now we are returning to the light. Our journey home is not instantaneous. We drift back through the interstellar medium, that thin, cold dust and gas that fills the space between the stars. We pass through vast ethereal clouds of hydrogen, glowing a faint, rosy pink, illuminated by the young hot stars being born within them. These are the stellar nurseries, the cradles of creation. And it is here, in the gentle swirl of cosmic dust, that we are reminded of a profound and beautiful truth. The very same forces that lead to the creation of a black hole are also the forces of our own beginning. A massive star, many times the size of our own sun, lives a brilliant but fleeting life. It burns through its fuel with unimaginable ferocity, and in its core, it performs a kind of alchemy. It fuses hydrogen into helium, then helium into carbon-carbon, into oxygen, and on, creating the heavier elements that make existence as we know it possible. When its fuel is spent, the star collapses under its own immense gravity. This collapse can be so violent that it triggers a supernova, an explosion that for a brief time can outshine an entire galaxy. In that spectacular cataclysmic death, two things happen. If the star is massive enough, its core will continue to collapse, forming the very black hole we have just left behind. But the outer layers, enriched with all those newly created elements, are blasted out into space. Carbon, nitrogen, oxygen, iron, a fine, precious dust scattered across the galaxy. This stardust drifts for eons, mingling with other clouds, until gravity, patient and persistent, begins to pull it together once more. A new star forms, a gentler, more stable star, surrounded by a swirling disk of that leftover element-rich material. And from that disk, planets coalesce, rocky worlds, gas giants, and perhaps a small blue world perfectly placed where those elements can come together in even more complex ways. Feel that for a moment. The iron that flows through your veins, giving your blood its color and its ability to carry oxygen, was forged in the heart of a dying star. The calcium that gives your bones their strength, the carbon that forms the backbone of your DNA, the oxygen that fills your lungs with every gentle breath. Every atom of it, save for the most ancient hydrogen, was born in a stellar furnace and cast out in a supernova. The same event that creates an endpoint, a black hole, is also the seed of a new beginning. Destruction and creation are not opposites. They are two faces of the same cosmic process, a slow, eternal dance of matter and energy. You are, in the most literal sense, stardust. You are the universe made self-aware. The story of the black hole is not a separate, distant tale. It is your own origin story. As we continue our journey, the sheer scale of the galaxy unfolds around us. We see spiral arms, majestic rivers of stars and gas sweeping around the galactic core. We pass globular clusters, ancient dense spheres of hundreds of thousands of stars glowing like cosmic embers. We see the remnants of other supernovae, intricate web-like structures of expanding gas that look like delicate paintings on the canvas of space. Each point of light is a sun, and around so many of them we know now are planets. Worlds of ice, worlds of fire, worlds of gas, and maybe, just maybe, other worlds like our own. The sheer numbers are humbling. Hundreds of billions of stars in our galaxy alone, and hundreds of billions of galaxies in the observable universe. To contemplate this is to feel our own smallness, and that can be a profound source of peace. The anxieties, the worries, the pressures of a single human life, they find their proper scale against this backdrop. They do not vanish, but they are held in a larger context. To be a tiny part of such an unimaginable whole is not to be insignificant. It is to be part of a story so grand, so ancient, that its telling spans billions of years and unimaginable distances. And now a familiar light begins to grow brighter ahead. It is not the fierce blue-white light of a young massive star, nor the dim red glow of an ancient dwarf. It is a steady, warm yellow-white light, the light of our own sun, our home star. As we draw closer, the planets of our solar system resolve from points of light into worlds. We see the immense stormy presence of Jupiter with its great red spot and its family of moons. We glide past the impossible beauty of Saturn, its rings a shimmering, delicate disk of ice and rock catching the sunlight. We see the cold, distant blues of Uranus and Neptune, and then we see the inner worlds, the red desert of Mars, the cloudy veil of Venus, the cratered face of Mercury. And there it is, a swirl of blue and white suspended in the black, Earth. From this vantage point, there are no borders, no divisions, no signs of the frantic, busy lives being lived on its surface. There is only a single beautiful and fragile-looking sphere, a living world. The thin, shimmering layer of its atmosphere is all that separates the vibrant life on its surface from the cold, airless vacuum of space. It is a testament to the sheer improbability and preciousness of our existence. On this one small stage in a vast cosmic arena, everything that has ever mattered to any human being has taken place. Every joy and every sorrow, every hero and every coward, every creator and every destroyer of civilization, every king and every peasant, every mother and every child. All of it on a mote of dust suspended in a sunbeam. Let our perspective drift down now through that thin, protective veil of air. We descend through the high, wispy cirrus clouds made of ice crystals, then through the lower, fluffier cumulus clouds. The continents and oceans take on shape and texture. We see mountain ranges wrinkled and ancient. We see the dark green of forests and the pale tan of deserts. We see the sparkle of sunlight on the surface of an ocean. The scale continues to shrink, from the continent to the region, from the region to the city, from the city to the neighborhood. The sounds of the world begin to filter in, not as noise, but as the gentle hum of life. We drift down further still, past the roof of a familiar building, through a window, and into a quiet room. And here, the journey ends. Right here, in this present moment. The grand cosmic voyage across galaxies and eons resolves into the simple, peaceful space you now occupy. Feel the gentle weight of your body. Notice the quiet rhythm of your own breathing, an echo of the cosmic cycles of expansion and contraction. The in-breath drawing in the oxygen forged in a star, the out-breath releasing it back into the world. You are the endpoint of this journey, the awareness that traveled to the edge of a black hole and back resides right here. The curiosity that propelled us on this exploration is one of the most fundamental aspects of being human. We look up at the night sky and we wonder. We build tools from telescopes to theoretical equations to extend our senses to see farther, to understand more deeply. This journey into the nature of a black hole is part of that ancient human quest for meaning, for understanding our place in the cosmos. We may never physically travel to one, but in our minds, in our shared pursuit of knowledge, we can touch the edges of reality. And what have we learned? We have learned that the universe is more strange, more beautiful, and more mysterious than we can possibly imagine. We have learned that the deepest darkness is necessary to reveal the brightest light. A black hole is the ultimate darkness, a place where light itself cannot escape. And yet, its very presence allows us to see the structure of space-time, to test the limits of our theories, to witness the raw power of gravity. Without the silent, empty blackness of the night sky, we would never see the stars. Without the darkness of the unknown, there would be no impetus for the light of discovery. The darkness is not an absence to be feared. It is the canvas upon which everything we see is painted. So let the vastness of space hold you. Let the knowledge of your cosmic origins bring you comfort. You are a child of the stars, a temporary beautiful arrangement of ancient matter, gifted with the astonishing ability to look back at your own source and wonder. The story of the universe is not something happening out there. It is happening right here in the beat of your heart, in the thoughts that drift through your mind, in the quiet, steady act of being. You are a way for the cosmos to know itself. And in that, there is a profound and lasting peace. The journey from a single point of light in our ancestors' sky to a deep understanding of gravitational collapse is a testament to the power of human curiosity. We have traveled through space and time, not with a ship, but with the vessel of our collective intellect and imagination. We stood at the precipice of an event horizon, contemplated the end of time, and journeyed through the stellar forges that created the very substance of our bodies. The black hole in the end is more than just an object of immense gravity. It is a mirror. It reflects the limits of our knowledge, the depth of our wonder, and the intimate, unbreakable connection we have to the grand, unfolding story of the cosmos. May we always carry a piece of that quiet cosmic perspective with us, finding stillness in its vastness and meaning in its mysteries.